Let's talk about the Sierra Nevada, the Basin and Range Province, and a brief geologic history of Western North America. Let's start with the active subduction that's taking place beneath northernmost California, Oregon, and Washington, where the remnant of the Farallon Plate, the Juan de Fuca Plate, is still subducting beneath Western North America. And this is giving us melts that are intruding into the North American continental crust and creating the active volcanoes that include Mount St. Helens, Mount Rainier in the Seattle and Tacoma area. This subduction of that oceanic Juan de Fuca plate brings fluids and the metamorphic reactions that are driving off metamorphic fluids into the overriding mantle wedge, that piece of mantle that is above the subducting oceanic plate. That lowers the melting temperature of the mantle wedge, and it generates basaltic melts that are partial melts of mantle rock. Those melts enter the continental crust, where there are some processes of differentiation that are taking place to change those basalts into more andesitic or even rhyolitic magmas and lavas that feed these volcanoes. This video is going to show you this kind of process where fluids are being brought down with the subducting oceanic plate and magmas are being generated by partial melts of mantle peridotite to feed a chain of active volcanoes. You see the magma rising up, feeding chambers beneath volcanoes, and then subsequent eruptions of lavas from those volcanoes. You can watch that one more time. You'll see that sediments, along with fluids, are being dragged down the subduction zone. That, along with the metamorphic processes in the rocks in the deeper part of those subducted oceanic rocks, are driving off fluids that are structurally bound within the minerals. That water enters the overlying mantle wedge, lowers the melting temperature of the mantle peridotite, and generates those basaltic melts that then differentiate into andesites and rhyolites in the continental crust. We've been talking about the volcanic arc that is currently active beneath northernmost contiguous U.S. In northernmost California, Oregon, and Washington. And that's the subduction of this small Juan de Fuca plate beneath North America. And this movie shows the development of the tectonic setting of Western North America in the last 20 million years or so. What you see is these arrows are pointing to the tectonic plate motions. So the Pacific plate is moving northwest. The Juan de Fuca plate is moving northeast. Those are going to shift during the movie so that you can see that the stresses in the earth are changing. You'll also see some place names: San Diego, Santa Barbara, San Francisco, just as locations that you can identify with and follow their path as the tectonic plate boundaries change. And then you're seeing these triangles here denoting subduction. You see them down here at the bottom of the screen too. The arrows are on the overriding plate, so we are looking at oceanic crust that's subducting beneath continental crust. You're also seeing spreading ridges. So these bold red lines are spreading ridges, and The lines in between are the transform faults that separate different segments of spreading ridge, or they're called fracture zones. So you're going to see those change and move over the last 20 million years. And you're also going to see the growth of the San Andreas Fault. So let's watch. You're seeing the block that contains San Francisco and Los Angeles move northward along with the rotating Santa Barbara block. We're going to watch this a couple of times. This is showing you northwestward movement of the Pacific Plate as the San Andreas Fault develops. The San Andreas Fault is shown here in the red line. And so it is east of San Francisco, Santa Barbara, LA, San Diego. And you're also seeing the development of a spreading center in the Gulf of California behind Baja, Mexico. And somewhere between the Gulf of California and the Salton Sea that is east of San Diego, there's a transition from the spreading center to the San Andreas Fault. Let's watch one more time. I want you to watch how those different parts of California, denoted by the place names, move northward, and how the spreading begins in the Gulf of California and opens up the Gulf of California and separates Baja from mainland Mexico. Okay, everything's moving north. Spreading is going to start soon. It's showing between 8 and 4 million years. This is really approximate, where spreading starts in the Gulf and the location of the modern San Andreas Fault is shown. One last time so that you can see that it is the ancient Farallon plate that is being subducted beneath Western North America, and that subduction stops when the ridge is subducted that's pushing that plate. The San Andreas Fault starts to grow, and so the positions of the subduction zones is changing as the San Andreas Fault lengthens and moves northward. You watch those triangles disappear as the San Andreas zips northward, pulling everything on the Pacific Plate side with it. Okay, and this diagram shows a time progression from 30 million years to 20 million years, 10 million years, and then present day, what the configuration of these various plates is. And 30 million years ago, you're seeing this ancient Farallon plate subducting beneath the North American plate. So this subduction zone is present up and down Western North America. That's giving us the volcanic arc that form the Sierra Nevada batholith and the volcanic rocks that are on top of that batholith, and that today form the volcanoes in Oregon and Washington. As that Farallon plate is subducted, it is being pushed or pulled, whichever way you want to think about it, by the spreading ridge with the Pacific Plate behind it. As that ridge intersects Western North America, let's move to 20 million years ago, the ridge has been subducted, and the Farallon plate is now divided into two smaller plates, the Cocos Plate and the Juan de Fuca Plate. Those are just relics of the Farallon plate. But once that ridge is subducted, we've started to develop the San Andreas Fault. as the new plate boundary between the Pacific Plate and the North American Plate that results from a change in the stresses from the change in the direction of plate motions between these various plates. So it's about 25 million years ago when this first intersection starts and when we start to grow the San Andreas. And it starts in the south, probably around Los Angeles or just north of Los Angeles near the Grapevine. And as time progresses, the San Andreas grows longer and it moves northward. And then today, we can see that the San Andreas runs from somewhere near the Salton Sea up toward northernmost California and the Mendocino Triple Junction, and that we have the modern day subduction of the Juan de Fuca plate. The Pacific plate motions are moving to the northwest, and so causing this right lateral strike-slip motion along the San Andreas Fault. And that we have a young ocean basin being formed in the Gulf of California, where we have a spreading center opening up Baja California from mainland Mexico. And then also the southernmost remnants of the Farallon Plate being subducted beneath Mexico and driving the volcanoes in Mexico and Central America. To look at it in a slightly more simplified view, you can see that we've got, again, this modern subduction that is taking place beneath southernmost Canada, Washington, Oregon, northernmost California. The San Andreas Fault that's moving from the Mendocino Triple Junction here down east of Los Angeles, Santa Barbara, and San Diego. And then it disappears somewhere north of the Gulf of California, where spreading starts and is opening up this modern ocean basin. And I said that the San Andreas Fault started at about 25 million years ago. It's closer to 28.5 million years. And we know that from dating of volcanic rocks that are at a piercing point at the Pinnacles National Monument that match up to volcanic rocks in Southern California. And we can date those, and we know that those are about 25 million years. And that the volcanism migrated northward. And so this diagram is showing where the San Andreas was at certain times. So at 15 million years ago, it was at about this latitude, south of Monterey Bay, at about Monterey Bay 10 million years ago, at San Francisco and the peninsula around 7.5 million years ago, and north of Point Reyes 5 million years ago, and then until modern day when it's at the Mendocino Triple Junction. And that's what's giving us the end of the transform fault right here at the Mendocino Triple Junction. And then leaving us with this last bit of Farallon Plate, still driving an active volcanic arc. If we take a step back and look at the North American Plate versus the Pacific Plate boundary on a smaller scale, you're going to see the spreading ridges in the bold red lines in the ocean and the subduction zone against the western North American continent. And we'll start at 85 million years ago and move toward the present day. You'll see the Farallon Plate is getting subducted beneath western North America. the San Andreas grows and separates that old Farallon plate into the Cocos down here and the Juan de Fuca plate up here. Let's watch it again. I'm going to stop it right about here. And we see that that ridge that's pushing the Farallon plate is just about to intersect Western North America. That's when the San Andreas is going to grow. It hasn't quite happened yet. If we move forward in time a little bit, you'll see the San Andreas form in about 25 million years and grow and move Baja and Los Angeles northward. The last movie shows us closer in. You'll see the Pacific plate off to the left here with directional arrows showing that it's moving to the northwest. The Farallon plate with directional arrows moving to the northeast. And the spreading ridge and fracture zones separating the two plates, as well as a subduction zone along the western edge of North America, and the timeline that starts just after 40 million years. And we're just going to watch this whole process go one more time. So about a little after 30 million years, about between then and 25 million years, the start of the San Andreas, the northward motion of the San Andreas, and the shrinking Farallon plate that is now the Juan de Fuca and Cocos plate. Last time. That Farallon plate is subducted, the San Andreas grows, spreading behind Baja and in the Gulf of California starts, and we have right lateral strike submotion on the San Andreas. And that's leading us to the geology that we have today in California. We have the remnants of that active subduction in the Sierra Nevada arc. We have the rocks of the coastal ranges, which, the circle is too large, but broadly are comprised of sediments and high pressure, low temperature rocks that were in the subduction zone, and the intervening valley, that is the Great Valley, the flexural basin in the front of the volcanic arc. And then we also have the spreading that's taking place in beneath the Salton Sea, where the start of that spreading center in the Gulf of California begins, as well as spreading in the Basin and Range in southeastern California. So we have the arc, the coastal ranges, and the valley in between that are related to subduction for the most part. We have spreading that is related to opening of the spreading in the Gulf of California, as well as the continental rifting in the Basin and Range, that are probably related to the plate motions that have changed since the subduction of the Farallon plate stopped and the development of the San Andreas fault began, because that right lateral strike motion is driving the Pacific plate off to the northwest. The North American plate has a smaller plate motion also off to the west, but generally we are seeing stretching in the Basin and Range and stretching in the new ocean basin that's trying to form in the Gulf of California. This is somewhat redundant, But we're seeing those same geomorphic provinces. They're related to those tectonic events. And the uplift of the Sierra Nevada was in part accomplished by this later spreading in the Basin and Range, because there is the westernmost normal fault in the Basin and Range right up against the eastern Sierra Nevada. And that's uplifting the Sierra Nevada and dropping down the basin, that basin that is the first basin in the Basin and Range. We have this sedimentary basin in the Great Valley, and those accretionary terrains that are in the coast ranges, but that were also uplifted because of transpressional motion along the San Andreas. And what that means is that the San Andreas, while it is a right lateral strike-slip fault, there is a vertical component, that a small vertical component every time that fault moves, that gives us uplift of those coast ranges. So those are relatively young features. So right now we have the modern geologic map of California that relates strongly to what was happening in the Mesozoic. This is a Mesozoic cross section, and you see the Farallon plate being subducted, the fluids entering the overlying mantle wedge and causing the volcanism in the Sierra Nevada, this four-arc basin that forms the Great Valley, and the subduction complexes along the coastal ranges. To compare the two, the geologic map in that cross section, broadly, we're seeing the red rocks that are the arc related rocks or related to the Sierra Nevada batholith, the yellow rocks that are part of the four arc basin in the Great Valley, the pale green rocks that are the subduction complex rocks, and purple rocks that are a bit harder to see because there are fewer of them, dotting the eastern side of the subduction complex, that are ophiolitic material related to the subduction of that Farallon plate. Now I'll put the Mesozoic cross-section next to the modern cross-section of California. And you'll see, again, the Sierra Nevada batholith here being uplifted by normal motion on the faults that are bounding the western side of the Basin and Range. You see the Coast Range mountains here that are the subduction complex rocks and ophiolitic material that are uplifted in part because of these transform faults or strike-slip faults that are forming the plate boundary between the Pacific and North American plates. That small amount of transpression and uplift along those strike-slip faults are bringing up the Coast Range. And then we have a relic of subduction also recorded beneath the Great Valley in some oceanic crust that is imaged there. And I'll go into how that oceanic crust got there momentarily. I like this view somewhat better just because it's more of a cross-sectional view. You can see the normal faults bounding the eastern Sierra Nevada, the four-arc basin formed in front of that volcanic arc, and then the coastal ranges that are comprised of the Franciscan complex in large part and the ophiolitic material related to that Mesozoic subduction. The Basin and Range is a wide feature spanning from eastern California across most of Nevada and into Utah and Idaho, even down into Mexico. But this series of sort of north-south basins and ranges are this continental rift zone that is similar to the East African rift, where it's not a plate boundary, but it's the early stages of stretching that might lead to opening up of a new plate boundary in a small ocean. So the Basin and Range and East African rifts are in this first stage of development of an ocean basin, where you get the normal faulting to form the basins and ranges, and that thins the crust and causes volcanism and underplating of partial melts from the magma, gives you bimodal volcanism of rhyolites and basalts. The second stage might get advanced to the point where you actually open a small ocean and have decompression, melting, and extremely thin lithosphere driving spreading. And that's like the Gulf of California or the Red Sea. And then finally, if that were to continue, you would end up with a mature ocean basin with a wide ocean, a well-developed mid-ocean ridge, and passive continental margins on its flanks, kind of like the Atlantic Ocean or the Indian Ocean. So along Western North America, there have been 4 kinds of plate margins at any time during the history of North America. And these are 4 types of ocean continent margins that have existed here at various times in the past billion years. And the 4 kinds we have are an Atlantic type that is a passive margin that existed here in the early Paleozoic. And that is where there's no plate boundary. It is a period of sedimentary deposition. In the late Paleozoic to early Mesozoic, we had a Japanese type subduction zone with an arc that is offshore and a sea between the volcanic arc and the mainland. From the late Mesozoic to the Tertiary, we had this Andean type of plate margin with a subduction, with an ocean continent subduction zone, and the arc that I've been describing, that's the Sierra Nevada. And finally, a California type margin, which is a transform margin where there's no subduction and no spreading. So as I've discussed already, the Sierra Nevada batholith is forming in the Mesozoic to give us this third kind of Andean type margin. I'm going to go through some steps about over the history of the geologic development of Western North America and describe each of these what's going on during each of these times in the last billion years. Before 700 million years, we didn't have a continental margin here. The North American craton, this brown area, was a stable part of the continent that's been so for the past 600 million years or so. We had a deformed craton in purple surrounding that craton interior. And then there was an accretionary belt in green that where other terrains were being added to North America over time. In the Proterozoic, the west coast of North America was attached to another continent. It may have been Australia or Antarctica. And it hadn't been a continental margin since at least 2 billion years. And it wasn't until around 800 million years that that continent rifted away. And it was along an irregular margin that truncated the old age provinces and established a western boundary of the continent. From the Precambrian to the early Paleozoic, so before 375 million years ago, we had the Craton area here in pink with allochthons, so foreign terrains that had been added on to the continental margin. And then what is currently Northern California, Western Nevada, Oregon, and Washington was underwater. Between 700 and 400 million years ago, we had an Atlantic-type passive margin. And as I described, that's a time when we had sedimentary deposition. So through the mid-Devonian, it was a stable passive margin. It accumulated a thick pile of clastic, so continental material, and carbonate sediments that's up to several kilometers thick. And those Proterozoic to Paleozoic sediments are still comprising much of the rock that is exposed in Western North America today. Between 400 and 250 million years ago, we had a Japanese-type offshore subduction. So there was an island arc off the coast, forming a chain of volcanoes with a sea in between that island arc and the continental margin. The ocean offshore widened and became older until it was unstable, and subduction initiated sometime in the early Paleozoic under this offshore arc. And then there was a steadily closing sea adjacent to Western North America. So from the Ordovician and Silurian Japanese-style arc to the Middle Devonian when that ocean basin was closing. That offshore arc collided with the North American margin in the late Devonian, and a new subduction zone initiated offshore. And you also see in this diagram that after we accrete those arc rocks to Western North America, we also get a polarity in subduction change. So we went from a westward directed subduction to an eastward directed subduction sometime in the early Mississippian. And then what it looked like, if we were looking at a map view, are the deformed edge of the Craton rocks, and then these series of thrust belts off to the west where we have these accreted terrains during that time. After a couple of arc polarity reversals, the same thing happened in the early Triassic, and it brought a new sequence of oceanic rocks to be deposited on top of the older rocks. And that accreted island arc underlies the western Sierra Nevada batholith today. So we're looking in this area here. So the Sierra Nevada arc was superposed on older accreted terrains, and so in this diagram you're seeing all of these accreted terrains separated by different thrusts, and the Mesozoic arc, that's the Sierra Nevada arc, superimposed on top of that. When we had that, after we had that polarity in subduction change and the new Andean type of margin setting developing. And that whole arc, that Mesozoic arc, runs from Canada down into Mexico. After Triassic time, the polarity of subduction remained normal, so that the North American continent was the upper plate. And the Andean type continental margin arc formed, and it's built on the basement of the Precambrian North America, the Paleozoic Maya-geocline. So those are those sediments that were deposited when we had the passive margin in the Paleozoic. And the older accreted arc terrains. The dip angle of the slab was initially pretty steep, and the arc was rather close to the trench, and there was relatively minimal deformation deep into the continental interior. In the late Jurassic, another island arc terrain that was riding on the subducting Farallon plate collided with the North American continent. Subduction stepped out beyond the new terrain to the west to establish the new subduction system that lasted through the Cretaceous, and it generated the Franciscan Trench, the Great Valley Forearc, and the Sierran Arc. The Sierra Nevada batholith is the deep assemblage of plutonic rocks that formed underneath those arc volcanoes at the time. So it looked something like this. About 150 million years ago, we had subduction that was at a steeper angle, and we had melting happening beneath eastern California. And then the angle of subduction changed to a more gentle angle, and that pushed the arc east so that we had magmatism happening under western Nevada about 100 million years ago. Another result of this was that the trench, the subduction trench, shifts west, probably during the late Jurassic. And what happens is we trap some of the oceanic crust beneath the Great Valley rocks and that form ophiolitic material that's been imaged beneath the sedimentary rocks in that forearc basin. And then the coastal ranges are comprised of these Franciscan rocks. That there are several belts of these Franciscan rocks that include bluish facies, high pressure, low temperature rocks, lower grade green schist facies rocks in melange type setting, so a mixture of serpentinite and sedimentary rocks, gray wackies with knockers or big blocks of metamorphic rocks within it, ophiolitic material in the Great Valley group, and then lower grade rocks closer to the trench side of this complex of subduction rocks. About 50 million years was the end of subduction, and in the Cenozoic, the subducting slab became completely horizontal, probably because of the progressive decrease in age of the subducting Farallon plate. So the Farallon plate was becoming younger as the ridge approached the trench. It was more buoyant crust. It resulted in the end of volcanism and deformation far inland, so the Rocky Mountains, and the emplacement of metamorphic rocks under Southern California. So these two cross sections here show the steeper subduction and then this more closer to horizontal subduction that resulted in deformation reaching in toward the Rocky Mountains. The slab, when it became flatter with time, it was a wide arc that propagated inland and was farther from the trench, and it caused that compressional deformation behind the arc. More recently, 50 to about 25 million years ago, we had a series of events that included extension in the Great Basin, so the Basin and Range Province. And you'll see these lines here showing volcanic fronts 50 million years ago, 45, 40, 35, 25, 20 million years ago that were related to the extension in the Basin and Range. Volcanism moved toward the south and spread along with extension that formed the core complexes that are across the basin and range. And we also had rotation of Western Oregon and the Klamath into their current position. After about 25 million years ago, we've developed the San Andreas Fault. It began in the south about 25 million years ago and moved north. The spreading had already started in the Basin and Range. That extension continued after 25 million years ago and continues today. Magmatism and eruptions that generated the Columbia River basalts, and perhaps even related to Yellowstone volcanism, was taking place. And the Mendocino Triple Junction migrates north as the San Andreas grows, and it shuts off the volcanic arc as it goes. So the active volcanism is also migrating north with the San Andreas. And that leaves us with modern California, that is a region of really complex geology that's reflected in the topography that we see and gives us all this diversity in geologic provinces that we can drive out in not so many hours to see.